Good day, Math 30-2s. Today we are adding and subtracting rational expressions. This is a continuation from last day where we were multiplying and dividing. Now, last day with multiplying and dividing, there were arguably two quick steps: factor and cancel. And as a caveat, we had to state those non-permissible values. Today we're adding and subtracting rational expressions, which is going to look similar but feel entirely different because the process for adding and subtracting fractions is very different than multiplying and dividing. Now, multiplying and dividing, if this was a multiplication sign, we would simply say 1 times 4 and 3 times 3, and we're done. Adding is a little bit more complicated because if we had a pizza broken into 3 pieces, and we added 1 piece of that size and 4 pieces of that size, we would have a total of 5 pieces of that size of a pizza broken into 3 pieces. Now, notice again that the denominator stays the same, but we're adding the quantity and almost a size for that denominator spot. Now, for part B, a pizza cut into 3 pieces and a pizza cut into 4 pieces is going to be very, very different. Here's one slice of pizza that is a third. No, we've got 2 of those. But here is a pizza cut into quarters or 4s, and this is the size of a pizza slice cut into 4s. And those are different sizes. It's really hard to add together a quantity where those sizes don't really match. So what has to happen is we have to find a way to divide this pizza into smaller slices where maybe we can actually find a common sized slice. Without visualizing too much, what we're looking for is for that bottom number to somehow match, and that's representing the size of that pizza. So what we're going to do is find a way to make that 3 and the 4 similar in looking at their factors, their multiples. So multiples of 3 are 3 times 1, 3 times 2. We can just skip count as well. 3, 6, 9, 12, 15, and so on. Multiples of 4 are 4, 8, 12, 16, and so on. And we're looking for the first one, the lowest common multiple, which is a 12. We ultimately want to get these numbers to have a 12 on the bottom, and this is going to allow us to have a 12th of a pizza cut into 12 slices will actually share a similar size. Now, to make this fraction 2/3 look like something over 12, we have to make this fraction have some bigger numbers. I can make this by having that denominator 3 being multiplied by a 4, the 2 multiplied by a 4, creating a 8 over a 12. So 8 over 12 is going to represent the same as 2/3. If I multiply this 4 by a 3, that'll get us to a 12. 3 times a 3 is a 9. And now we've got 8 over 12 and 9 over 12. I've got 8 pieces and 9 pieces, and they all share that same size. We've got 17 slices of a pizza cut into 12 pieces. This is adding fractions in its, we'll say, traditional way. Even if we don't know the size of that piece, but it's a variable, they match, and we can add these together. 4 plus 3 is a 7 over a. It's that denominator that stays the same, and it's that top numerator which actually adds together. Now, the letter D is different. 3a and a. Those denominators do not match. We can get them to match, just like we did above, by multiplying the denominator by a number. Right now, if I were to just write a 3 there, and I multiply that a by a 3, they match. I can multiply this by a 3 to keep this number the same in its value, and now the denominators match. I've got a 1 plus a 3 times 3, all divided by a 3a, and now we've got a 10 over a 3a. And now this actually is simplified. Even if we have a binomial x plus 1 and an x plus 1, those match. 7 over x plus 1. Now, right now, these look very, very different. 2x plus 2, x plus 1. They look incredibly different, But factoring has been a strategy employed before, and I'm actually going to do that again because even though these look very different, at their core, at their sort of root, they share something. If I factor out a 2, I'm left with an x plus 1. Now if I factor out that 2, I can actually see they share something. They both share an x plus 1. If I write a 2 out in front, and I multiply this top right by a 2 as well, those denominators match. So sometimes, as a good tip, factor if you want to see a potential common factor. That's funny. A greatest common factor. And so the top is a 1 plus a 6 over 2x plus 1, which final answer leaves us with a 7 divided by a 2 times an x plus 1. We didn't cancel anything, so I'm actually not overly concerned right now about stating those non-permissible values. But if I wanted to say x cannot be a -1, I could, but I can still see it. So I'm not going to worry too much about that right now. So there's a few to try, and this logic of potentially maybe factoring if needed. I know I can't really factor much, but multiplying to get to our common denominator. So a good tip is to factor if possible. The question mark for if possible. And a second tip is to multiply to get common. So I see an 8, I see a 4, and we're going to think about the numbers, the coefficients, separately from the variables for just a moment. So I've got an 8, I've got a 4. I can get this 4 to become an 8 if I multiply this bottom one by a 2. So I'm going to write these back in as they currently are, so we have a little bit more space. And I'm going to multiply this by a 2, top and bottom, because I'm really multiplying this by 2 divided by 2. I'm multiplying it by 1. It doesn't look like a 1, but its value is a 1. So now this says 8, this says 8, great. This says x squared. I need to always go into bigger numbers when we do these. So I'm going to multiply this bottom by an x, and now this says x times x, that's an x squared. This is x squared. So now if I multiply the top by an x as well, so those match, I now have an 8x squared, 8x squared. Denominators match. So we tidy this up a little bit and say 3 plus a 2x on the top, 8x squared on the bottom, 8x squared on the bottom, 3 plus a 2x. Those are not like terms because one has an x, one has a 3. They need to have the exact same variables or terms to match. Over an 8x squared, final answer added together. Now, I did say we have to multiply to get ourselves common. I see an x plus a 1, and I see an x. It would be incredibly convenient to add a 1 and add a 1. But there is a challenge in dealing with fractions and adding to say things are the same. Just to give you a rough idea of why that doesn't really work, what if I were to say 1 divided by 2? What if I wanted to make things bigger or different? Am I allowed to say plus 1 and keep things the same? 1 plus 1 is 2. 2 plus 1 is 3. Is 1/2 the same as 2/3? No. As a decimal, this is a 0.5. As a decimal, this is a 0.6 repeated. Those do not match. We're not allowed to add a number to get what we want. We're allowed to multiply by a number, like times by 1, times by 2 on the top, times by 2 on the bottom, and keep things consistent by multiplying, but not by adding. So I can't really add a 1, I have to multiply. And this one's actually kind of tricky because an x and an x plus 1 are totally different. Imagine if x was the number 5. Then what's the number on the left side? A 5 plus 1. If this is a 5, then this is a 6. Those are very, very different numbers. How are 5 and 6 kind of common? What's related? 5, 10, 15, 20, 25, 30, 6, 12, 18, 24, 30. 5 times 6 is your common multiple. To get these to match, I actually need to write that x plus 1, pretend it's the 6, on the right side. I need to multiply an x over here, pretend it's the 5 on this side. So this is like a 5 and the 6, 5 and the 6. Now they match. The x and the x plus 1 are very different terms. So now we've got a 2x on the top plus a 1x plus 1, and the denominator is an x times an x plus 1. We can tidy up that top a little bit and call it a 2x plus 1x. That's a 3x plus a 1. And the denominator, I'm going to leave that together so I can see the restrictions if needed. But that is a simplified expression for two very different denominators that look they have a lot more in common but really don't. So sometimes we're going to see numbers that we have to piece together like a 6 and a 4, and these are monomials. So we think about the numbers, we think about the letters differently and piece it together like we did up here. Here we've got a binomial and a monomial, and that we have to think about like they're very, very different things. So for this one, 6 and a 4, we're trying to get that to a common multiple. 12 would get us there. So if I multiply this by a 2 and a 2, multiply this by a 3 and a 3, I see an x squared. We have to multiply to get bigger, so I need to multiply this by an x, multiply this by an x, and this gives us on the very, very top a 5 times a 2 is a 10, 1 times a 3x is a 3x, and this is all divided by a 2 times a 6x squared, and a 3 times 4 is a 12x squared. That is our common 12x squared. And for this one, a 2x plus a 1 is totally different than an x. And so just like we did above, there is no way that we're going to add a 1 or times by a 2 to get these to match. These are very, very different terms. And so I can multiply by a 2x plus 1, top and bottom, multiply by an x, top and bottom, and this gives us a common x times a 2x plus 1 on the bottom. And on the top, I've got a 1x or an x, and then we're subtracting a 2 bracket 2x plus 1. Now, we do have to be very, very mindful of this, because when we're subtracting all of this, we have to make sure that that negative impacts all of this. One way we can do this is to make this negative 2 value get distributed in. So on the very, very top, we've got an x subtracting a 4x, 2 times 2x. So subtracting a 4x, but we're also going to put this negative 2 times the 1 and say minus 2. Often people will forget to call this a negative 2, and that's a very common mistake. It does tidy up a little bit further on the top. 1x minus 4x is a negative 3x minus that 2 over x times 2x plus 1. Lots of opportunities for some small mistakes. We'll do a couple more just to see some examples, but we're getting into the place where we've got a lot of the strategy in place and it's just being exposed to some common mistakes. Again, 2n plus 1 and n minus a 3 up here, incredibly different, and the only way to get there is by multiplying by the opposite factor, by the opposite denominator. And n minus a 3 on this side and n minus a 3. So now our denominator is going to look like a common 2n plus 1 and an n minus 3 in whatever order you like. We're multiplying. And here we've got a 3n multiplying by an n minus 3. So I'm going to distribute that in. 3n times n is a 3n squared. 3n times a negative 3 is a negative 9n. And we are subtracting a 4 bracket a 2n plus 1. I'm not going to rush this one because I again see a subtracting all of this, so the negative is going to have to impact all of that. So 3n squared minus 9n minus 8n minus a 4, all divided by a 2n plus 1 n minus 3. And just to tidy up that top, the like terms, there's a 3n squared, there's a negative 17n, and then a minus 4, and the bottom will keep in its factored form so that we can see those restrictions more clearly. Final answer. So we're going to make sure we can tackle some of the most challenging ones, factoring to get a common denominator. Now, in this case, it looks like we've got something totally different than this one. Again, I can't subtract to get what we want, but what I can do is factor if things look like on the denominator they can factor. I can factor out an x on the bottom left here, and in doing so, I can actually see they share an x. They both share the exact same letter. By introducing an x minus 1 right next to it, I can make them look exactly the same. Factoring, again, appears to be a great first step. So our denominator is going to match x times x minus 1, and the top is going to be a 3 plus a 1 times, I don't know, 1 times doesn't change anything, so an x minus a 1. Like term, 3 and a negative 1 is going to be an x. 3 minus 1 is a plus 2, divided by an x minus 1. Final answer. Factor. This time we have a difference of squares. A reminder that when you're doing adding, subtracting, and multiplying and dividing in Math 30-2 in Alberta, we only have to worry about a difference of squares or a greatest common factor type of factoring until lesson 4.5, which is next. So we can factor this difference of squares to see x plus 4, x minus 4, 4 over x plus 4. Now it appears they were very different, but they actually share an x plus 4 and an x plus a 4. So if we introduce an x minus 4, top and bottom on the right side, we actually have a matching denominator. This gives us a 32 plus a 4x minus 16 on the top, and our matching x plus 4x minus 4 on the bottom. And so we have a 4x. 32 minus 16 is a 16, all divided by an x plus 4 and an x minus 4. It is actually quite rare, but it is possible that after you get to the very, very end, there is something that could cancel. Incredibly rare, but with a little bit of foresight, you might see, hey, if I take a 4 out of the top, I'm left with an x plus a 4, an x plus a 4, x minus a 4. Hey, those x plus 4s actually could cancel. This is even simpler. 4 divided by an x minus 4, and then I do get to state some restrictions that x cannot be a negative 4, and I'll throw in a positive 4 for the other one. But this could actually be a bit of a simplifying question as well. Not as common when that happens, but it's very, very possible, especially considering we've already seen it. Now, there's a couple more for you to try that are very, very, very similar to these two above. So give those a try, and there are some questions you can try from the textbook if you like. Otherwise, this was adding and subtracting rational expressions. Good luck.